Hi! In this video, we'll go back to the start and briefly discuss the beginning of modern astronomy, followed by a beginner-friendly introduction to the coordinate system, which helps astronomers locate objects in the sky and tell them which ones will be visible from a given location at any time of the year. So join us as we figure out how to make sense of the map of the universe. So without any further ado, let's begin. Let's begin from the start. Claudius Ptolemy described his geocentric system and argued that in its position at the center of the universe, the Earth must be immovable. Ptolemy argued that since all bodies fall to the center of the universe, the Earth must be fixed there. Otherwise, falling objects would not be seen to drop towards the center of the Earth. Again, if the Earth rotated once every 24 hours, a body thrown vertically upwards should not fall back to the same place as it was seen to do. Ptolemy was able to demonstrate, however, that no contrary observations had been ever obtained. As a result of his arguments, the geocentric system became dogmatically asserted in Western Christendom until the 15th century, when it was supplanted by the heliocentric, that is, the sun-centered system proposed by the Polish astronomer Nicholas Copernicus. In Ptolemy's system, the celestial objects in the solar system rotated around the Earth in the following order: Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn, as shown here. However, he realized that the inequalities in the motions of these celestial bodies required geometrical explanation in order to account for their movements in terms of uniform circular motion. Over the course of time, aided by models by his contemporary mathematicians and geometers, Ptolemy introduced several concepts to explain observed phenomena such as the retrograde motion of planets. Nicholas Copernicus came about at the turn of 16th century and proposed his heliocentric model of the solar system. His theory immediately brought order to the planets and explained many observations. For instance, the planet Mercury is never seen more than 28 degrees east or west of the Sun, and similarly, Venus no more than 47 degrees away. This clearly establishes that their orbits are inside the orbit of the Earth. Hence, they are also called inferior planets, and their maximum separation from the Sun is called the greatest eastern or western elongation. The outer planets can be observed to a distance of as much as 180 degrees from the Sun, and this position is called opposition. This could only occur if these planets were orbiting outside the Earth's orbit, and therefore they are called the superior planets. Copernicus predicted that the inferior planets can also pass in front of the solar disk, a phenomena known as inferior conjunction. Earth and the retrograde planet are like race cars on an oval track. Earth has the inside lane and moves faster than, say, Mars. So much faster that it makes 2 laps around the course in about as much time as it takes Mars to go around the Sun once. About every 26 months or so, Earth comes up from behind and overtakes Mars, as shown in the diagram here. So as we pass by the red planet, it looks like as though Mars is moving up and down in the sky. Then, as we move farther along our curved orbit and see the planet from a different angle, the illusion disappears and once again we see Mars move in a straight line across the sky. This apparent erratic motion is called retrograde motion. The illusion also happens for other superior planets like Jupiter, which are farther away from the Sun relative to the Earth. In astronomy, timekeeping is done via 2 major periods: the sidereal time and the synodic time. Sidereal time is the time taken by a planet to complete one rotation on its own axis relative to the distant stars, which are assumed to be fixed. Synodic time, on the other hand, is the time taken by a planet to complete one rotation around its own axis relative to the star it is orbiting. The Earth's sidereal time is 23 hours 56 minutes 4 seconds, while the synodic period is the solar day, which is 24 hours. The two periods are different because in the time Earth has completed one rotation about its own axis, it has also moved along its orbit around the Sun. The Sun drifts eastwards by around 1 degree with respect to the fixed star every day of the year. There are 360 degrees in a circle and there are 365 days in our year. So, with respect to our clocks designed to measure the solar day, the same star rises and sets 4 minutes earlier each day. That is so because the star moves around the Earth in 23 hours 56 minutes, which is its sidereal time period measured with respect to the fixed stars. And in this sense, it is also the true rotation period of the planet. In other words, we can say that the synodic period is the time interval for a body to achieve the same elongation configuration with the Earth-Sun line. The formulae shown here can be used to find the sidereal or synodic time period of other planets using one of these two quantities along with the same for Earth. The same idea is applicable to the Earth-Moon system as well. The Moon completes its orbit around the Earth in 27.3 days, which is its sidereal period, corresponding to the Earth's sidereal period of 365 days and a few hours. But in this time, the Earth has gone around the Sun by around 30 degrees. So, to come to the same configuration, the Moon actually needs an extra 2.2 days, because of which the time difference between two successive new moons is 29.3 days. To understand the day-to-day changes in the position of the stars, we need to understand the orbital motion of the Earth around the Sun. The sidereal period of Earth around the Sun is 365.25 days, which implies it moves around 1 degree every day. So, to bring the Sun back to the same position relative to the Earth on 2 successive days, Earth should actually move by 361 degrees. So, it takes the Earth around 4 minutes to cover that extra 1 degree. Since other stars are much farther away, they don't seem to move much relative to us. But each star rises approximately 4 minutes earlier each night. The vernal equinox, that is, the day on March 21st, is the point at which the Sun crosses the Earth's equator moving northwards, and the southern crossing point is called the autumnal equinox, which occurs on September 23. These critical days in the calendar officially announce the arrival of the transition seasons in India, the spring and the autumn respectively. The summer solstice occurs on June 21, when the Sun reaches the ecliptic's northernmost point, while the winter solstice occurs when it hits the southernmost point on December 21. If you have ever seen the star catalogues, you must have noticed that the coordinates are mentioned as J2000. That is because the current standard epoch is J2000.0. The previous one was B1950.0. In this context, B means the Basilian year, which begins when the mean longitude of the Sun is exactly 280 degrees. This always occurs very close to the start of the calendar year, but not always at the same instant. On the other hand, J means the Julian year, which is exactly 365.25 days long. J2000.0 represents midday on January 1, 2000, and every other Julian year begins at an exact multiple of 365.25 days from then. In 1984, the International Astronomical Union recommended that star positions should be calculated on the basis of Julian years rather than Basilian years. Julian years are named after Julius Caesar, who is credited with the first reform of the calendar. The year, more accurately the tropical year, is measured from one spring equinox to the next, an interval of 365.2421988 mean solar days. In the Julian calendar, Most years have 365 days with an extra day every fourth year, and as you know, that's called the leap year. Hence, averaging 365.25 days to a year with an error of 1 day every 128 years. While we all know about the rotation and revolution of Earth, there is another motion that our planet experiences. This is called precession. The effect of precession is that the north celestial pole is not stationary but makes a slow circle with respect to the distant stars, just like a spinning top before it comes to rest. It is the impact of precession that Polaris is less than 1 degrees of the north celestial pole now, but 13,000 years later it will be 47 degrees away from it. Precession also alters the position of the vernal equinox by around 50 arc seconds every year. Hence, it is necessary to record the epoch of observations for listing the coordinates. The presently used catalogue lists the coordinates as at noon in Greenwich on January 1, 2000. In the year 1609, an Italian scientist, Galileo Galilei, improved on a pre-existing design to build a telescope to observe the sky for the very first time. First of his design had an 8x magnification, but he soon refined the design to a 20x magnification with a convex objective lens and concave eyepiece. To know more about these optic elements, check out our video on telescopes. Amongst others, one of the key discoveries of Galileo was to find the moons of Jupiter. As of now, the IAU recognizes 95 moons of Jupiter, and the largest 4 are called the Galilean moons in honor of their discoverer. But once more and more objects in the sky were being identified, it became obvious that locating and identifying celestial objects in the night sky can be a daunting task without a proper coordinate system. Imagine being outside on a clear, dark night, surrounded by thousands of twinkling lights, each one a world in itself. The challenge of navigating the night sky is compounded by the fact that the stars appear to shift and change positions over time. This is due to the Earth's rotation and orbit around the Sun, which causes the constellations to appear differently throughout the year. A coordinate system, therefore, helps to account for these changes, providing a fixed frame of reference that allows astronomers to track the movement of celestial objects. The celestial coordinate system is a fundamental concept in astronomy, allowing astronomers to pinpoint the location of stars, planets, and other celestial objects in the vast expanse of the space. The ancient Greeks were among the first to attempt to catalogue the stars, but their system was limited and often inaccurate. As astronomy evolved, so did the need for a more precise and efficient way to locate and identify celestial objects. Imagine, like the ancient Greeks, that all celestial objects lie on the same sphere, that is, at the same distance from us. Then, to specify their position, it is sufficient to specify only 2 coordinates. But before we do that, there are certain quantities that we need to define. The zenith distance of an object x is 90 degrees minus a, where a is the altitude measured from the plane of horizon as shown in the diagram here. The meridian is a great circle passing through the observer's zenith and intersecting the horizon. The azimuth angle is the angular distance around the horizon from the north cardinal point to the vertical circle through the star X measured eastwards. But there is a problem, since the coordinates will change with observer's latitude and longitude, and also because stars rise 4 minutes earlier every day. So even when viewed from the same place, the coordinates will change for an object every day. In order to account for these changes, we need to move on to the R-angle coordinate system. Here, we imagine that all the celestial objects are on a sphere such that the Earth's longitude and latitude can be projected on this large imaginary sphere. The projection of the Earth's equator on this sphere is called the celestial equator, and the poles are respectively known as the north and south celestial poles. The celestial meridian is the observer's meridian, which is any great circle between the north celestial pole and the south celestial pole, but one that also passes through the observer's zenith and nadir, which is the point opposite to zenith, known as the celestial meridian. Remember, zenith is the point right above your head, so nadir is the point right below your feet. Now all stars rise in the east, move rightwards and set in the west. These are equatorial stars. The ones which are close to the north celestial pole never set and are called the circumpolar stars. When you see images of star trails like these, circumpolar stars, the ones which make the complete circle as viewed from a given location, are close to the center. By the way, what star do you think lies at the center of these trails? Let me know in the comments below. The angle measured on the celestial equator corresponding to the azimuthal angle is called the R angle. Since Earth makes a round of 360 degrees in a period of 24 hours, each hour represents 15 degrees. On the meridian, the R angle for an object is equal to 0 hours by definition. This means that the hour angle increases as the object moves westwards. The problem with this system, however, is that the coordinates are time dependent. This problem can be tackled by introducing the equatorial coordinate system, popularly known as RA and dec, or right ascension and declination. The declination in this case is the distance of star from the celestial equator along the meridian. This is very similar to the Earth's latitude. Basically, this is the height of the object above or below the celestial equator measured in degrees. The plus sign is used for the northern hemisphere, while minus is used for objects lying below the celestial equator, and each side measured from 0 to plus or minus 90 degrees, going from the celestial equator to either of the poles. The point on celestial sphere where the ecliptic intersects the celestial equator is called the vernal equinox. This provides a means to connect the sidereal time to the coordinates of an object. The local sidereal time is the amount of time that has elapsed since the vernal equinox last traversed the meridian. This implies that the local sidereal time is equal to R angle of the object. The other coordinate in the equatorial system is the right ascension or RA, and for a star, it is the angular distance between the meridian of star and the meridian passing through the vernal equinox measured eastwards. Traditionally, the RA was measured in hours. Here is a great way to recap and understand the various angles and terms we have discussed so far. I recommend pausing the video here and taking a moment to understand this concept, especially if you are a beginner. It would be a great exercise to pick up the coordinates of a star and figure out if it would be visible in your sky, and given your latitude and time of observations, where to look for it. Now here are the coordinates for some famous stars. Note that basically the declination tells you where to look for a star. For instance, I am very close to 23 degrees latitude, and we know that once every 24 hours, all stars will pass through the meridian because the Earth rotates on its own axis once every 24 hours. Now, if a star has its declination close to 23 degrees, then all I need to do is to look directly above my head at the time of its meridian crossing. But if a star is further away, say 43 degrees declination, then I will have to look 20 degrees lower than the zenith, or in other words, 70 degrees from the top of my head, in the north direction because the star is 20 degrees closer to the north than I am. And between the horizon and the point above your head, there are 90 degrees in total. The right ascension is calculated from the point where the ecliptic meets the celestial equator and is marked as RA of 0 hours. That means if a star has an RA of 6 hours, it is basically 6 hours behind the Sun on the day of the vernal equinox, that is March 21. So, if the Sun rises at say 6 am, the star will rise 6 hours later at noon. And as the Sun sets at say 6 pm, the stars will set 6 hours later at midnight. This means this particular star will be observable in my sky from 6 pm to 12 am on March 21. Similarly, you can work it out according to your latitude and positions of some of the stars given here, or the one that you can look up in star catalogs or on the internet. But you know that the Earth moves around the Sun by 30 degrees every month, and there are 15 degrees in an hour. This means that our star, which was 6 hours behind the Sun on March 21, will now only be 4 hours behind it on April 21, catching up by 2 hours every month. That is why I have written here that round to the nearest even hour, which gives you a good handle on where to look for the object. Now that we have understood the coordinates, here is a common method of estimating the degrees on the sky. Now, of course, every person's hand size is different, so you have to figure it out for yourself if you're very different from the averages mentioned here. To give you a reference, the full moon is about half a degree in size, that is 30 arc minutes. There are other coordinate systems as well which are not very frequently used, and therefore I have not discussed them in this video. For instance, here is the galactic coordinate system based around the center and the plane of our galaxy that is used by astronomers to specify the position of objects mainly within our own galaxy. The significance of celestial coordinate systems cannot be overstated, as they play a critical role in navigation, astrophysics, and of course our understanding of the universe at large. By providing a fixed frame of reference, these systems enable astronomers to track the movement of celestial objects, study their properties and behavior, and gain insight into the fundamental laws of physics. I really hope you enjoyed this little discussion on the history of astronomy and the coordinate systems. Do like, share, and subscribe to our channel and share our content with other astronomy enthusiasts. I will see you next week with another video on astronomy. Until then, take care.